In today's lecture, we will learn how to choose a pricing model. As you can imagine, in the industry, there are multiple models, and one has to decide which model to choose in which scenario. You have to think of many different aspects once you decide that one model is of particular interest and particular importance once you talk about derivative pricing. You have to look at the calibration, you have to look at the pricing, you also have to look at the risks. Today's lecture, we will cover some of those important aspects. Let us take a look at today's content. First, we will talk about different possibilities of choosing pricing model. Here we'll take a look at different numerical techniques that can be used to perform pricing, and we will look at the aspects like calibration, speed, accuracy, features like callability, etc. Then I will provide you some motivation of using Fourier transformation. This is, of course, will be related to the first point once we talk about efficient evaluation and in which scenario we need to have model or we need to have pricing technique that allows us to evaluate prices in a very, very fast way. We will discuss in this lecture, in this course, multiple models for which we don't know analytical solution, however, for which we are able to find characteristic function. This is a kind of introduction to the topic of characteristic functions. So here we will derive characteristic function for the Black-Scholes model. Later, this characteristic function is going to be used in Fourier transformation. Of course, for Black-Scholes model, it's really not necessary to do any Fourier transformation because we know analytical expression. However, this is more for illustrative purpose. We will discuss also today affine jump diffusion processes or affine diffusion processes. The processes, so a class of models that for which we are able to find characteristic function. So what kind of conditions your stochastic system of stochastic differential equations needs to satisfy such that we know that the process belongs to the affine diffusion processes, or it's affine class of the affine diffusion. And once we have a model which belongs to this class, we know for certain that the characteristic function can be derived. We'll also show you how to how to derive characteristic function for high dimensions. And finally, we will discuss affine jump diffusion processes. So you can see here we have affine diffusion processes, we have affine jump diffusion, so extension of the framework to include additional jumps. As we already have seen before, jumps can be very handy once we talk about generation of smile and skew. So by adding jumps, we can have more flexibility. We add more flexibility to the pricing framework, and often we are not able to find analytical solution for those densities, for those distributions, but we can find it via characteristic function. How to choose a pricing model? If I give you a task of pricing of a derivative, first thing you have to do is to decide what model to choose. And that's a rather tricky and difficult task. Let us take a look at the wider context of pricing and how to choose a proper model. If we think of any financial institution, we typically have a front office and back office. This is you can think of a separation from trading activities and also back office, so model, basically maintaining of models, maintaining of trades, and bookkeeping. So in front office, this is a place where it's typically associated with a trading floor where trades takes place. So when there's a client, for example, coming to a bank and would like to buy a derivative, this trade would basically take place in the front office. Then this trade will be later transferred into back office. So once you have a trade, and this trade very often will last for many years. This means that over that period of time, it has to be maintained. Risks need to be monitored, position has to be also controlled and maintained. So, and especially if you think of interest rate swaps or kind of mortgages, when you think of, you have a number of payments that will take over the whole period of time, the period of time of the life span of the mortgage, for example. This means that if there is if some payments are missing, this has to be maintained. Somebody has to control it and do something which has to react if something goes wrong in the payments, for example, and that takes place in a back office. So when we think of front office, it's typically pricing and selling products. So if there is a client coming to a bank, uh, it there are two options basically. A client may ask for a particular product, or client, for example, could describe a problem that client has. For example, if it is a pension fund, and pension fund would like to control the risks, they may ask bank or any financial institution how they could, what products do they recommend to maintain or fit the purpose of the risks that they would like to manage. Then front office would design, typically it's called structure, a product that will fit the purpose of the client, and that will be then evaluated. So model will be chosen, model will be used for pricing, and then the trade will be booked. And then, of course, something to keep in mind that front office typically would decide about the model that is going to be used for trading, but models which are developed by financial engineers or quantitative analysts, those are not models which are essentially random models. Those models need to be validated. This means that if there is a model, model can give you a price, but of course there are many models that could give you different prices. So one has to decide what model is most appropriate for trade that front office would like to do. And that is related to the validation process, validation of prices. So it's not only about choosing a model, but also about the implementation of the model, whether a model is suited for the risks and whether it performs well. It also has to be sufficiently fast, because imagine if you have a trading book with hundreds of thousands of trades, and each of those trades to evaluate will take months or let's say hours, then you can think of whole evaluation taking months. And that could be very slow and not acceptable, especially that every day, every night, there is some kind of process called end of day process, where all the risks, all the trades are aggregated, put together, and all the sensitivities, all the risks are reported in the morning for next day trading. So as you can imagine, that's relies heavily on the complexity of models, and also models need to be suited for the trades that front office performs. If, for example, imagine a situation when you choose a rule model, you can either you can offer a price to a client which is better or worse. You could think that if the price is better than client expected, or for example, the value of a contract is undervalued, then clients, of course, will be happy, but that would mean for the bank or financial institution that there is a loss. So that's not desired. On the other hand, if a pricing model gives higher price and client has to pay more for that product, essentially maybe you make money in short term, but you may destroy the relation with the counterparty, with the client. So in long term, you may lose a client. So that's also not desired. So overall, bank or any financial institution prefers to have to make clients happy and also maintaining the risks in some limits. So you prefer to have continuum of trades, continuum of profits with a satisfied clients. So let us take a look at a few steps that need to be taken once we talk about pricing. First, we start with a specification of some financial product. So this is, as just mentioned, it can be due to a client coming to a bank asking for a product, or a bank designing, structuring a product for a client. So then once we have a product which has some payoff, this means there'll be some payments happening in the future, or there's one payment happening only once, it doesn't really matter. Given the specification of a product, and if your product depends on one asset class or multiple asset classes, then we go to point number two, where we need to specify stochastic differential equations for all the risk factors which are that our payoff depends on. So if you have an interest rate product, then your SDE, the stochastic differential equation, has to involve process for the interest rates. If you have stocks, then you need to have a number of stochastic differential equations for stocks, and so on. So that's the second part. There you specify SDEs. And of course, at this point, you also have to be careful, choose models which are, especially if dealing with high dimensions, that they are sufficiently fast and accurate. So that's basically, I would say, a little bit of art, but also after this course, you'll be having good feeling what are the possibilities, which model it is more suitable for which payoff. Then, once we have a payoff and we also have specified risk factors, then we need to define the model, the price. So this is something that we have done already before. It can be done via PIDs or PDs, or it could be done in an integral form. We can also think of pricing with Monte Carlo. This is something which we also have discussed using Feynman's cut theorem, when we have an expectation of all the future payments discounted today under risk neutral measure. So that part, as you can imagine, if we have a payoff with 50, 60, 70 years, this evaluation doesn't need to be super fast. It has to be fast. That if we have many payoffs as the same as the one we started with, then indeed it has to be fast enough, but it doesn't need to be super fast. Super fast part comes in point number 4, when we need to calibrate our model. Imagine if you have a payoff and you price it, you do it only once. Of course, you do it multiple times if you calculate your sensitivity, so risks to all the risk factors. But in general, you just do it once to get a price. However, if you calibrate your model, this means that you have to evaluate your model hundreds of times, or if not thousands of times. So then, essentially, every millisecond that you can gain from the evaluation, it will pay off in the calibration process. So imagine that every day, once market data changes, or something has changed, even we go one day further in time, then model has to be recalibrated to new market data. And that needs to be very fast. And today's lecture, and also follow-up lectures, will be about this very important point number 4, where we concentrate on very fast techniques for calibration. And that will be based on Fourier techniques. Okay, then we have point number 5. So once we have chosen a model, we can do pricing. We have calibrated the model, and this is very important that it's performed very fast. Now we have point number 5, where we do pricing of a product of interest. So once we have a model, we can use, for example, Feynman cuts with to evaluate Monte Carlo paths or some PIDs, whatever we come up with, to price 3. So once we have 3, this is a specification of a payoff, we calibrate, and now with calibrated parameters, we have to go to number 3 essentially, and we price number 3. And then the last point, so once we perform the pricing, we can actually sell the product, but then it comes the second part, when I just mentioned, is about maintaining of your payoff. You have to hedge it on a daily basis, weekly basis, sometimes even monthly basis, but this also requires that the payoff has to be, your model has to be continuously recalibrated and used for hedging purposes. Now let's take a look. I did also some specification of what type of pricing and type of solutions that we have. So if we have a model, we came up with stochastic differential equations, we have a payoff, then we can have either exact solution. So this is something that we have seen already in a case of Black-Scholes model, for example, arithmetic Brownian motion. Those simple models we can typically price analytically. We can have a semi-exact solution. So this is, for example, perturbation techniques. So those two you can consider that are very fast because they typically are in a closed form. So like exact solution, we know that Black-Scholes model can be done with evaluation of some normal CDFs. And that's very fast. Semi-exact, it means that it's also done very fast. However, there is some kind of error, because it's not exact, it's semi-exact. So some elements could be approximated or have to be done numerically, but that typically it's closely related. That's typically very fast. And then if you go to numerical methods, and then we have really whole spectrum of different techniques that we can use for pricing. We can do, for example, Monte Carlo simulation. So this part depending on the payoff, we may choose Monte Carlo simulation. From my experience, this is one of the most common approaches for pricing, especially if we deal with high dimensions. So we know that if somebody considers PDEs, he likes PDEs, it will be very difficult to define a partial differential equation and solve discretization of your PD once you have more than 1 or 2 or 3 dimensions. And if you have, let's say, S&P 500, imagine you have 500 different stocks. So partial differential equations and discretizations could be very, very expensive to do that. Monte Carlo is much nicer. Then we have trees. This is also limitation. It's similar as PDs. It's very much limited to dimensions. On the other hand, those two techniques are having great advantage that essentially sensitivities, so Greeks like delta, gamma, vega, those are done essentially at low cost, and they are always very smooth. So Monte Carlo simulations are good because they have a lot of flexibility, but of course it's a Monte Carlo, so this means that you have likely some random noise. Later in this course, we will spend a lot of time on Monte Carlo simulation and different techniques, how to perform simulation, even in high dimensions. And the last part that we will concentrate actually in the coming lectures will be about FFT, Fourier-based methods. So those methods are it's a slightly different between the two. So Monte Carlo you can use for high dimension for pricing. PDs has advantage of Greeks, but FFT is typically associated with extremely fast pricing. So fast speed here is the top element. So if we go back, calibration is about the speed. We need evaluation which is performed very, very fast, and for that reason we typically concentrate on FFT methods. What is also very important is that if we have a client who came and wants to buy an exotic derivative or complicated trade, this could be done very difficult. Could be very difficult for FFT for implementation and also derivation. So FFT is typically it's a derived technique for simple payoffs. For Monte Carlo, it's much more suitable, or for example, for PDs. So the contract that we want to price, if it's very complicated, it's typically priced with Monte Carlo, not so much with FFT. FFT is about simple products. However, if we think of calibration, imagine we have this complicated payoff. It's very unlikely that we will be able to calibrate our model based on that value, because it's very, let's say, it's tailor-made product. So not too many trades as such in the market. This means you cannot use those products to calibrate. So what we typically do, we calibrate used European or very simple contracts. So this comes with the relation that we have market. A market is arbitrage free. This means that if we have a model, some system of differential equations, we calibrate those differential equations to the market, to let's say call and put options. From that, we obtain set of parameters for the model. Then we can use those parameters for more advanced, more complicated pricing. So typically you can think of calibration and pricing. It is something like extrapolation of your calibrated parameters. So we calibrate based on liquid instruments. However, once we talk about pricing of exotic derivative, then we take those parameters that we have calibrated in let's say FFT terms, in a FFT way, and then we apply those parameters for pricing of an exotic derivative. Yes, so in general, it is difficult to find analytic solution for multi-dimensional correlated stochastic differential equations. So this is what I told you, that if we have we have a basket of multiple stocks, it's very difficult to find analytical solution, especially if all the assets are correlated. For that, one could consider Monte Carlo approach. Those are really straightforward. We will focus, I think, about 2 lectures purely on Monte Carlo techniques, how to do it efficiently, and how to control your convergence. However, there are some downsides of Monte Carlo simulation. The first one, of course, is that it depends on sampling seed. So imagine that because Monte Carlo is about random samples, this means that every time you perform, you revalue your contract, then you get slightly different output. And that means that you have some error associated with that. Of course, if you have enough number of paths, enough number of samples, then every time once you evaluate the trade, the value, the difference between the prices will be smaller. And that's typically what you like to have. If your value of a trade changes by 10, 15% every time you evaluate it, that's not really good. And this means obviously that you have done something wrong. And typically you didn't have enough samples or actually there's something wrong with your code. So therefore we have Monte Carlo involves sampling error. So we sample, we don't get exact solution, it's an approximation. And of course, if we have a very high dimension, we also need to have a rather powerful machine to do that. Of course, these days there is a lot of attention on GPUs, on parallelization, such that the Monte Carlo sampling, for example, can be done very fast. So I would say these days this is not such a big concern. However, these two, so sampling and the randomness effect, this is something that you have to learn in this course, how to look at it and how to control it, how to improve the convergence. This is very, very important. There are also alternatives, yeah. So alternative methods need to be used. So alternative to Monte Carlo methods are, for example, Fourier. This is what I just mentioned. Fourier techniques are typically used for calibration. And although for complicated models, distributions are known analytically, the corresponding characteristic function can be often derived semi-analytically. This means that for Black-Scholes model, for example, we were able to find pricing the density, so probability distribution function, so probability density function of a stock, of stock T, and we got it analytically. We know that in a case of Black-Scholes model, it is log nul. So we know that we should write slightly differently. ST, ST is log nul. This means that the PDF and CDF, we know it explicitly. However, in a multi-dimensional case, or even in sometimes in a much more advanced one-dimensional cases, we don't know it. So we don't know the distribution of the underlying stock process. However, we can think of characteristic function. So we can imagine that we have a class of models for which we know PDF analytically. So let's say analytical. For this model, this is the family of characteristic functions, and then this is the wider scope of the solutions for models which have solutions. So as you can imagine, for example, for Black-Scholes model, we may know characteristic function, and also we know model analytically. However, there are multiple models, and this is something that we will learn today. There is a number of models for which we don't know analytical solution. However, we know the characteristic function. So those are analytical solutions here, and this is a subclass of models for which we know the characteristic function. Of course, there could be also models somewhere here that for example, models which don't have characteristic function. However, we know analytical solution. So characteristic function is typically associated with certain class of models. So those models are affine models. But indeed, there could be models for which are not affine, which are not linear, for which we know the analytical solution. So maybe this block here should be moved more to the left, where we have a characteristic function and also nonlinear models. But however, we concentrate on affine models. Later it will be clearer what that means. But imagine the situation to summarize that we have for some models analytical solution. There are more complicated models for which we don't know analytical solution, but we know characteristic function. And characteristic function still, although maybe it's closed form, it requires computation, it requires some numerical technique to invert it to get to the PDF, for example, for the density function for a stock. This means we need a step in between. We need a model in between that will bring us from a Fourier space, from characteristic function to density. This is objective also of this course, of the follow-up lectures. So we may have characteristic function, and then we concentrate how to get to CDF or PDF how to get a density of a stock once we have characteristic function. And we would like to do it very fast. And for that reason, we use fast Fourier transformation. Let us take a look at the details of Fourier transformation, Fourier methods in general. So, as already mentioned, those techniques are computationally very efficient, very fast. They're not restricted to Gaussian-based models. So, actually, for any model, any random variable which has characteristic function, we are able to use Fourier transformation. And it should work as long we have a characteristic function. Characteristic function is defined in this way. In a few slides, we will go into more details about this formulation. Characteristic function we have already seen before is for jump models that was discussed previously. And once we have a characteristic function, then effectively we are able to use Fourier transformations to go back to density. So once we have a characteristic function, we can switch to density. And once density is given, we can compute option prices. Here in particular, we talk about density. So you see, we concentrate on density of at some x at some time t. So normally, when we think of a process, right, stochastic process, we talk about paths. Let's say random realizations of our stochastic process, but here we have a density. So the question is how to relate these two. We have a given time t, we will have a density, right? And this density is this density here. So as you can see, the density that we observe at a given point t, this is the one we want to recover using Fourier transformation. So it is not about the propagation in time. This is only about the density given at one point in time. So this density here, we could also write it's a density of a random variable x. It's a t, capital T of x. So the capital T here is very important because it's at given point in time. This is why Fourier transformations are applicable and very handy to deal with pricing of European type options, because in European option, we only rely on one particular maturity. So there is no dependence in this direction. We don't, payoff does not depend explicitly on realization of paths, but only depends on the distribution, marginal distribution at the maturity time t. And that is used for calibration. So this is why Fourier transformation is very handy and very efficient once we talk about the calibration. In probability theory, characteristic function of a continuous random variable x equals the Fourier transform of the density of x. So this is something to keep in mind. This is something what we actually see in this formulation. Okay, here I have prepared two graphs. On the left-hand side, you can see blue line shows us a PDF, probability density function of a normal distribution. So here we have a normal distribution with 10, 1. This means mean is 10, it's here. And then we have a variance of 1. Orange or red, it's a CDF, so it's a cumulative distribution function. And on the right-hand side, this is a figure presenting characteristic function. So you see characteristic function is in 3D because we have u. So as you could actually see here, we have argument u. And here there is an exponential term. It's a I, so it's a complex number. This means that if you would like to plot it, we have to think of a real part and also imaginary part. So this is kind of interesting to, it's not really clear how to link one to another. So you cannot really see it. In order to get a density at a given point here, you essentially will need to integrate the whole Fourier space. When you think of a characteristic function, you can think of a tube where you see a spinning of this curve. In the code, in the book that you can, if you search for the characteristic function, there's also a code to generate those plots. And once you play with those parameters, you will see the number of rotations, it changes. So I think if a volatility will be very, very small, number of rotations will increase significantly. It's about the frequency in let's say signal space, number of signals that you will have, the frequency of the signal. So how you can think about it is that bigger the volatility, so bigger the variance, you have essentially distribution which is smooth, which is basically slowly diffusive. That means that number of spins, so number of iterations will be very few. So here we had one, so we see 1, 2, 3, 4, 5 basically. But once the volatility is very small, so this means that your distribution is very peaked, then you will see that there are hundreds of thousands, maybe even iteration spins of this in the tube. So this is interesting to see. I highly recommend to play with the code and to generate those graphs. However, although maybe they are insightful, but they are not, they are handy, nice to see, they're not so much insightful. Only one thing that you can use once you plot characteristic function is the point where there's no more oscillations. So for example, we could say, okay, oscillations actually stop at this point. This means that it's around here, should be around 3.5. This means that if we think of a density, so essentially density is an inverse of this. This tells us how to choose the domain for u, so how to integrate, because we know that after u reaching 3.5, the value essentially is 0. So from the insightful part or the useful part of this figure, it can be showing you the limit where you should integrate in order to recover your density. Okay, a few important points. Continuous Fourier transform is one of the most important transforms in the signal analysis. So this is something what I already have mentioned. It transforms one function into another one, which is called the frequency domain representation. So we can actually switch from this density to this Fourier space, and this depends, of course, on a frequency of your characteristic function. So you can see this wavy kind of behavior. In the specific case, both domains are continuous and unbounded. So this is technical condition. There are several common conventions for defining Fourier transform in a complex valued Lebesgue integrable functions. And it's also related, like I just said, about signal processing. Here are more details, so the technicalities. The first very important element is that if we talk about characteristic function, we already saw that in order to get characteristic function, we essentially need to integrate density. This means the density needs to satisfy some technical conditions. In this case, it has to be limited to L1, so the first moment, absolute moment, exists, so it's finite. And then and the definition of characteristic function is simply an expectation of an exponent of RUX. So it's a characteristic function, properly right, of x, of an argument u. It is this expectation. So you see there is a characteristic function, basically is an expectation of this random value. So if we follow just the definition, we can have it here. So it's a exponent RUX times the density of x dx. And this can be also written in this way. So by definition, density is just derivative of CDF with respect to x, as you can see. So if you substitute here, essentially dx will cancel, you will get dfx. Often you can also read, sometimes people write mu x. Don't be confused, it's just essentially shows you what measure is used. So this is, in this case, is the CDF. In implementation, it doesn't really matter. You can either, if you like to just integrate density in order to get characteristic function, then it doesn't really matter whether you integrate with density or integrate on a CDF. Of course, in practice, it's more common that we will go opposite direction. So for given a characteristic function, we'll be looking at density. In this case, we'll just start it with defining things. So for given density, we look for characteristic function, but this is just an example. Inverse will just simply be with a minus sign here. There are a few handy properties that it's very important to keep in mind. Those can be very useful. The first one is the relation between derivative of a characteristic function at 0 with respect to k derivative as essentially expectation of x to power k. So if you would like to have a k moment of a variable for which you know the characteristic function, It's simply kth derivative evaluated at u equals 0. So this is nice property to have. Of course, there is some again technicalities that any moment that we are interested in exists. Something which is more important, and I will explain in a few seconds why, is the following relation. So if we have a variable x defined as a logarithm of y, you can also think we have an x is a logarithm transform of a stock. Let's say it's a geometric Brownian motion, we take a logarithm. Then we have the following relation. So characteristic function of log y of u is equal to exponent. So this is expectation. So just the definition of RU log y. So this is definition. Then we find, okay, we know that there should, in order to find this expectation, we need to use the density. This is what we have here. And then you see that IU log y is simply log y to power IU. So things will simplify, and then we end up with an integral from 0 to infinity e y to power IU fy dy. And this is something very interesting, because what it basically says is that if right now I would substitute instead of u, so if I evaluate characteristic function at u equal to minus ik, so this I will just evaluate all the way and plug in there, we'll get the following expression. So characteristic function of logarithm of y minus ik is equal to integral of y to power k. This comes from the fact here that we would, if we substitute for u minus ik, then we have a I times I is minus 1, and then we have a minus, so it's basically, it's 1. And then we have a u, which is k. So this, and this term by definition is an expectation of a y to power k. So this means that if we have a characteristic function of a log of a variable, and typically when we talk about stocks and characteristic functions, we will deal with a logarithm, because we know that every stock that we deal with, it cannot be negative. So we always have this exponential element in there. So most of the time we have this will hold, that we can always do log transformation. Unless we consider a model maybe that allows stocks to be negative, but that's very unusual. But normally this is what the class of models we were considering. So you see that if I would like to have if y is my logarithm, so it's a log normally distributed stock, then kth moment is the characteristic function of a log of y evaluated at I minus ik. So this is very handy, because it means that I can calculate every moment of a stock, for which actually I could calculate a logarithm if I know the characteristic function of the log. So this means analytically, for example, for Black-Scholes, we know this characteristic function analytically. We immediately get all the moments essentially for free by just evaluating characteristic function. And that's very handy, especially once you have implemented your Fourier transformation, or you have implemented your characteristic function, you have a stock. So what you can also do is that if we have, maybe you remember from the past, we have an expectation of a stock t over mt. If we consider interest rates to be deterministic, this will be E minus RT. You have expectation of ST. So this is a Q measure. So this will be equal to E minus RT. And then we can use this property here. So it will be characteristic function evaluated at minus I and K, which is 1. You see? So once we have calculated our characteristic function, we are able to check whether an implementation is funded by this property. And we know that this has to be, because it's a martingale, it has to be equal to ST0 divided by MT0. So this property has to hold. And if we use the results from this term here, we know that characteristic function is minus I times e to minus RT, it has to be equal basically to ST0 MT0. MT0 is 1, so this is just ST0. So initial stock value. Let us now derive the characteristic function for the Black-Scholes model. As we already have discussed, working under the log transform, it is handy as it kind of linearizes the problem we were dealing with. It is also related to the, let's say in this case, when we had a logarithm of a stock of y, then we can easily relate characteristic function to moments. In general, when we deal with stocks, it is typically the case that we have to perform log transformation of a stock. Later in this lecture, it will be clearer why it is necessary condition. For now, it is, you can simply think of linearization of a problem that we deal with. Under the log transform, we have x, which is defined as log of s. So our payoff, our value, does not depend anymore as we had before. We have a v of s, we have a u of x. Let me write down the PDE that we had previously for the Black-Scholes model. So for the Black-Scholes, we had the partial derivative with respect to time. Then we had the drift term, so it was rs derivative with respect to stock, plus we had a half sigma squared second order derivative with respect to stock squared, and then we had a term corresponding to the risk-free growth of the portfolio. So this is minus RV. So once we have changed from stock S to log of stock S, we need to change variables. So this means that we have to change those partial derivatives. The first one is very simple, yeah, because our transformation does not depend directly on t, so it's just a derivative of v to t is derivative of u to t. Second, and the first order with respect to s, and second order, we have to apply just the chain rule. So derivative of u to x, x to s, and we know that since we deal with x to s, so it's a log transformation, derivative of a log of s is simply 1 over s, and then we have a derivative of u to x. And for the second order is the same. We just perform the first order of the first order derivative. So we just take this term and we compute a second derivative. Okay, and this is the term we have. So once we have those three terms, we can substitute into the PDE from the Black-Scholes. And this is what's happening here. So we have a derivative of u respect to time minus rs, and then we have 1 over s, so this term is coming here, a derivative of u to x, then half sigma squared s squared, and the second order derivative of the new variable, which is here. And then we have minus r u equals to 0. As we can see easily that many terms will cancel out, so this s 1 over s is gone, s squared here is also gone, and this is gone too. So right now, it simply becomes that our partial differential equation, as you can see, does not depend anymore explicitly. We don't have any terms of x or s in front of partial derivatives. So as you can see, log transformation essentially simplified our PDE. This is why it's so powerful. So before we had the derivatives, partial PDE with a lot of s's. So sorry, this was actually, I'm missing here s squared. So this is, please correct in your notes. So sigma squared s squared derivative of v to respect to s. And of course, this will be also included in this term. So by log transformation, we essentially linearize our problem. And this PD is much simpler to deal with. Especially now you can see that there's a few things we can also combine together. Okay. Another step what we do, it's a technical step. We define tau, which is equal capital time t minus t. So instead of essentially going forward in time, we go backward in time. It's a technical choice and doesn't really matter here. Okay, the substitution, of course, since we have derivative respect to time, so there will be a minus term everywhere once we have derivatives with respect to time. And one powerful statement, theorem that we would like to use right now. Later, I will provide you more details on it, but for now, we can use the result of Diffusion and Singleton, which claims that if we have a PD of this form, then the solution for this PD is given as the following equation. So we have u of xt is equal to phi u tau, and then we have exponent a plus b times x. A and b are some functions. We have to find them, but this is just a form that it will satisfy this PDE. Later in this lecture, we will discuss exact conditions for which this is indeed the case, that this expression of this form satisfies PDEs, the pricing PDEs we have. But for now, we can just take it as granted and we can just check it if it is indeed the case. So of course, as we had in transformation from S to X when we had log transformation, now we have to substitute. So we have this u to tau, and of course those derivatives. You see that we had derivative of u to tau, u to x, and ux squared. Phi function also depends on tau and x. So we have to calculate, if this is indeed solution, we have to calculate those derivatives to substitute to this PDE. And we also have a boundary condition. So at tau equal to 0, this means at the final time, the solution, the condition is to power I ux. So this is which comes from the theorem of Duffy, Pan, and Singleton. Okay, so we have to calculate these derivatives. Of course, since we deal with an exponential form, then the first order derivative of exponent will be just an exponent. So it's a phi, and then we have everything which is under the exponent. So we have derivative of a to tau times x, and derivative of b to tau. For x, it's similar. So we have phi times b, because those terms, they don't depend on x. And for x squared, we will have phi b squared. So now we have those terms. We have to substitute to this PDE. So we take this result and we plug in to this transformed PDE. Once we do that, after the substitution, we will end up with this expression. You see that every term in this expression relies on as a phi in front, so we can essentially divide all sides by phi. And this will be the following step. So we have the following result. We have a minus derivative with respect of a to tau plus x derivative of b to tau, and then we have some functions, some terms only by b, and then some constant. So now what we do, we order all the terms by variables we have. So we have only one variable x. So this term has to be 0. So derivative of b to tau has to be 0. And then if we collect all the remaining terms, then we have here, this also has to be, the quality has to hold. So only if this is 0 and then this term is equal to the minus of the rest, because we have minus sign here, then this is the necessary condition that will lead us to the solution of the PDE. So only one thing which is left right now, we need to find out what are the what are the solutions for those ordinary differential equations. So of course, for b and a, we just have to integrate using appropriate conditions. So since we know that the boundary condition that we have is u 0, and here we have, so at the final state, we have e I u x. So we know that at the maturity, or at the tau equal to 0, this term is equal to 0, and this term is equal to I u. So this is the boundary conditions for A and B for those of these. So we can write with boundary conditions B, this will be u 0 equal to I u, and A u 0 equal to 0. So those are the boundary conditions for those two ODEs. So of course, after integration, after using these boundary conditions, you can see that those integrals, you see that on the right-hand side, the term for a does not depend on a, so it's just a simple integral, and all those terms are constant. They are constant, they are not time dependent, so that's also rather trivial. And also we know the boundary condition for b, so this is trivial too. So this is the solution what we have found for the a and b functions. So we have I u for b, and for a we have essentially something like a drift term under log transformation times I u tau. We have also volatility term, which is u squared tau, and then we have a discounting part, which comes from r tau. After substitution, so once we take a and b and we substitute in this expression for a and b, then we arrive at the characteristic function, which is given of this form. So this is the methodology that we have used of of Diffusion and Singleton to find the characteristic function for the Black-Scholes model. Of course, ultimately, we are not interested only in Black-Scholes, because Black-Scholes case, it's a trivial case for which we actually know the analytical solution. So we don't need, in essence, characteristic function because we know the solution. So this is here more for testing and see whether we will arrive at the same expression. But this is also illustrative to indicate how what is the process in deriving those characteristic functions. So in the characteristic functions, we always have to check whether we can apply this solution to this PDE. So those are the conditions that we will discuss later in today's lecture. And once we have this, once this is the form of a solution, in order to find A and B, we need to determine number of ODEs. We need to solve some ODEs. And the complexity of those ODEs will depend on, of course, on the dynamics of the models. Typically, if we have constant parameters and one-dimensional case, then those ODEs are very trivial. If we have time-dependent parameters, as you can imagine, we would have some numerical integrations happening here. But in this case, it is very much straightforward. Okay. And this is, again, a figure, two figures presenting how this characteristic function for Black-Scholes model looks like. You see that our characteristic function depends on x, which is actually the initial. So here x, we have it should be x of t0, which is equal to logarithm of st0. So if you calculate this characteristic function, instead of x, is actually meant by logarithm of the initial stock value. And this is also what is presented here. So you can see log s and 0. And this tells me also that this figure shows you that after, let's say, u reaching around 30, then the characteristic function becomes this line. It's a 0, it's flat. So this will be the moment where your integral, in order to get to density, then you should stop your integration if your integral depends on a upper limit. Now we will formalize the conditions that system of stochastic differential equations needs to satisfy so that we will have a characteristic function of a given form. As you remember, for Black-Scholes model, the characteristic function was of form EA plus B times X. And this X is actually initial value at time t0. So now we will work with a class of models for which all of the characteristic function will have the same form. This class of models is called affine diffusion processes. So for every model, every stochastic differential equation which is in this AD affine diffusion class, the characteristic function will exist and will have the following form. So it will be always form of e to power a times plus b times x. In this case, actually, x is one-dimensional. In higher dimensions, it will be b1, x1, b2, x2, and so on. So it's always a generic form. But of course, we need to classify, we need to specify the conditions for which this is exactly the form of the characteristic function. So let us follow work of Diffusion and Singleton and give all those conditions. So we consider a system of stochastic differential equations. So it's not only one SDE, but it could be also a whole system of SDEs. So we have x, we have a drift term, which will depend on x dt, and we have a sigma term. Actually, this could be a matrix, because here we have a Brownian motion which is independent. So in practice, most likely you will work with Brownian motions which are correlated, but you can represent the system still in terms of independent Brownian motions. However, then your sigma matrix will need to involve special terms such that the Brownian motions will be correlated. We will discuss this particular condition, how to represent dependent Brownian motions in terms of independent Brownian motions. This will be discussed later in the lecture. But this has to do with matrix decomposition, so-called Cholesky decomposition, which allows us to transform correlated Brownian motions into set of independent Brownian motions. However, then we need to modify our volatility structure. So you can imagine here that volatility here is a matrix. A matrix depending on a number of x's and number of Brownian motions. In most of the cases, a number of Brownian motions we deal, it will correspond to number of state variables x. So if you have 5 stochastic differential equations, normally you would have also 5 Brownian motions. However, this is not requirement. You may have, say, 5 processes for your stocks, for example, but you may also have 25 Brownian motions. So there is no really condition. However, in practice, in the models that we will consider, and also in the literature, typically number of Brownian motions correspond to number of state variables. So here we have n processes. Here we also have n n Brownian motions and also n processes. And here are the conditions. So we have 3 conditions. However, one of them is crucial one. One of them is the most difficult to satisfy. So let us take a look at the drift. For the drift, we have the following. So we have a mu equals a0 plus a1x xt. So this means that the drift, which is here, it can only depend in linear way on x. So for example, we cannot have here x squared of t. So this is a condition that needs to hold, otherwise the processes that we will consider would not belong to this class, and characteristic function is not of this form. Very likely we cannot find this characteristic function at this moment. For example, if you have a Black-Scholes model, we would have a dst dt. Here we have rst dt plus sigma st dwt. So as you can see, this condition also would be satisfied in this case. So we have a0 would be equal to 0 and a1 would be equal to r. So then this condition holds for Black-Scholes case. Now we look at let's look at the third one. Third condition is about interest rates. So it has nothing to do with a drift for processes that we consider, but only about discounting. So at this case, in these models that we consider in this set of lectures, we have most of the cases we will be having constant interest rates, maybe time dependent, but in general, you could also have interest rates that are multidimensional and stochastic. So then we would have also the same condition R0 plus R1 transform. So this is a vector, and then we have here xt, which is xt is the space of the state of variables. So we could also have, of course, in this case, we have R0. If we have a constant interest rate, this will be only term that is left. This will be R1 is equal simply to 0, right? So this will be the case in our model. And so for Black-Scholes model, we also satisfied without any problems. The third and the most important condition is the condition regarding volatility structure. So here we have sigma x times sigma x. So you see that it's a matrices. You have to transpose this, and we will have after multiplying or squaring volatility, we also need to have a linear form of dependence on state variables. So this means that whenever after multiplying those matrices, the output that you will have would only need to be linear in x. It cannot be anything else. If you look for Black-Scholes model, for example, you see that we have, so let me go here. You will have a sigma bar transposed. So this is this term which we see here is equal to sigma squared s squared t. You see that it's squared. It can never be transformed, represented in linear form. We cannot have c0 plus c1 times s because we have s squared. So this means that if you look at the Black-Scholes model, just as defined, this model is not affine model, and that's a big problem. So, however, under log transformation, you see that we will have only sigma times Brownian motion. Then we only have this part left, so it's only sigma squared, which is constant. So then we have a c0, which is equal to sigma squared. Then after under log transformation, Black-Scholes model is affine. However, without log transformation, it is not. So then this is also the reason why we have defined the log transform in the previous part when we discussed the characteristic function and solution from Duffy, Pan, and Singleton. What Duffy, Pan, and Singleton says explicitly, so those are the conditions for the models for the system of differential equations to be affine. And what we have further is as following, that if we have a system of differential equations that indeed is affine, then characteristic function that we consider is the following. It's an expectation under measure Q. We have a discounting part, so it's an exponent of discounting, times E, IUXT, and then we have a filtration with a boundary condition. This is also what we have seen before. So this is the boundary condition. And the solution for this characteristic function, so this is basically a definition of characteristic function, actually definition of discounted characteristic function, with a boundary condition, has the following solution. So this is what we have seen before. It's an exponent of a plus b times x. So once we have SDs which are affine, then according to Duffy, Pan, and Singleton, characteristic function exists and is given of the following form. And this is very, very important. We have derived A and B for Black-Scholes model just simply by substituting characteristic function into the PDE, which gave us a system of ODEs for A and B. However, in a work of Duffy, Pan, and Singleton, this dependence on PDE and ODEs is more explicit, and it's stated as following. So the coefficients of functions A and B, they need to satisfy the following so-called Riccati type of ODEs. So this is important name, Riccati type of ODEs. And see that those letters here, we have R0, A1, C0, C1, A1, and R1. Those functions correspond to those coefficients which we get here in the decomposition. So we have a A0, A1, we have R0, R1, and then we have a C0, C1, which are matrices for the diffusion, for the volatility part. So once we determine those A's, R's, and C's, we can substitute them into this ODE, system of ODEs. And then if we solve those ODEs, then we have our characteristic function given in this form. Okay, so here's the example, something we have seen already before. Again, Black-Scholes model. We have R, we have a risk-neutral measure Q, we have a money savings account with the same R. Then we have the following PDE. This is the Black-Scholes PDE. And if we just follow the Duffy, Pan, and Singleton, the condition for affinity, so affine diffusion models, then we have sigma squared, so this is the volatility terms, and then we know already we have presented it will be sigma squared s squared. This process is not affine, so this is not affine because this is not linear. However, if we do perform the log transformation, we have the following SD. So this is also what we have seen before. We have a constant drift term. It's a R minus half sigma squared. And then we have volatility, which is also constant. You see nothing depends here on state variables. Then we have the following coefficients. So for the drift, we have R minus half of sigma squared. We have a zero dependence on the X, so it's just a constant. For volatility, we also have a sigma squared for C0. We have a 0 for dependence on the state variables on X. And for interest rate, we also consider just a constant interest rate. So R1 is simply 0. Then we know that the characteristic function is given of this form. We also know the ODEs from Duffy, Pan, and Singleton. This is the Riccati type of ODEs. After substitution, R0, R1, A1, A0, and then we have a C1 and C0. This is the system of ODEs that you arrive. We also know the boundary condition. As you remember, Duffy, Pan, and Singleton also gave us the boundary condition. So this is equivalent to what we have seen already for Black-Scholes case. And if we use those boundary conditions, we have the similar, actually, we have the form that we have already seen for Black-Scholes. So IU at 0 is BU 0 at time 0 is IU. So at the final stage, we have IU for B, and we have a 0 for A. And then we have the following characteristic function for Black-Scholes model. So again, characteristic function depends on initial value of a stock. So it's a log S0. We have a drift multiplied with tau times IU. We have a term corresponding to volatility, half U squared sigma squared tau. And we have a term which corresponds to discounting. So actually, formally, this characteristic function should be called discounted characteristic function. This is because of this term here. However, it does not really matter. You see that this term, it's constant, so we can take it outside the characteristic function. This is the same if we look here in a definition of characteristic function. So Duffy, Pang, and Singleton consider stochastic interest rates. This means that this term, it can be stochastic, but in our case, this is just a constant, so we can take it outside and forget about this dependence on interest rates, as this will be also this, then this term will be gone, and this will be gone too. Okay, so in this part we have discussed the conditions for affine diffusion, and we have also shown how to solve the ODEs. That ODEs that we have from Duffy, Pan, and Singleton, they are rather straightforward to integrate, to solve, and once we have the solutions, we can use them to derive the characteristic function. So essentially, we know the form of the characteristic function, we know the ODEs for A and B's, we only need to solve them and plug it into the form for characteristic function. Then we know exactly, explicitly what the characteristic function is. In practice, however, not always we are able to find A and B analytically. There are models like, for example, Schobel-Zoo, for which A and B are not known analytically. And this means that those need to be solved numerically. So this means essentially that for every argument you imagine, you have to perform integration. That could be time consuming and very expensive computation, because for every argument of a Fourier space, time integration will need to be taking place. So once you deal with those models, it is very important to choose those parameters or choose those SDEs such that actually ODEs that we have, they can be solved analytically and the form is explicit. It's very, very important. Under the affine diffusion framework, we can work with more than one dimension. And here is an example that we will consider right now. We have a 2D uncorrelated geometric linear motion processes. So imagine you have two stocks which are modeled by geometric linear motion. For simplicity right now, we assume that those processes are uncorrelated. This means that the Brownian motions in SDEs, they're independent. Yeah? So there is no correlation between W1 tilde and W2 tilde. Later on, we will also discuss the case when they are correlated, when there's a correlation between those two, and also this implies correlation between stocks or S1s and S2. We already know that if we define stock processes under geometric linear motion, those processes are not affine. So obviously we have to define, as the first step is to perform logarithmic transformation. So we consider x equal to the vector of 2 log S1 and log S2. And then we also have, after this transformation, we have two SDs with the same interest rate. So we know that those are two stocks. So this means that for both ds1 t and over mt and ds2 t over mt, in both cases, those dynamics, they don't have drift. So both processes S1t mt and S2t divided by mt, they need to be martingales. This is what we already have discussed. This is the condition that those processes need to satisfy under risk-neutral measure. So then we have those processes here, dx1 and dx2. The only difference between the two is that one has sigma 1 and one has sigma 2. So those are the, let's say, that's the money implied volatilities and the money volatility coefficients corresponding to these processes. The rest is the same. Okay, so we have two SDs. We have to follow affine diffusion or work of a Diffie Panen signal. We need to define those in terms of matrices. So in the matrix notation, we have the following terms. So this is just dx1, dx2. We have a drift term, and we have volatility. So you see that because there is no correlation, if we multiply this matrix by this vector, we have a sigma 1 dw1. For a second process, we have a sigma 2 times dw2. If you have correlation in the model, those terms would not be zero. So this would not be zero, and this would not be zero. There will be a correlation coefficient, for example, sigma rho, sigma 1 times sigma 2. That's typically what term we would see here and there, once we deal with correlations between variable motion. But this is not the case in this case. This is just a simplistic illustrative example how to find the characteristic function for more than one dimension. Okay, so if we follow affine diffusion, we have A0. So we have no A1 because there is no dependence on a state. We have R0, which is R, so we have a just constant interest rate. We have a C0, which is given in the matrix by diffusion. We again have no dependence on state variables. So C1 is 0, R1 is 0, and A1 is also 0. Following 2D case for characteristic function, we know that this is the form of the characteristic function we have. So we assume here that we are looking for 2D characteristic function. So we have multiple cases what we can consider. We can consider, for example, stock, which has volatility. However, we are interested in characteristic function only for stock. Then this means that we will have only U1 and U2 will be 0, because we don't really want to derive the density for, let's say, second process. In this case, we consider we would like to have a 2D density for both processes. This is why we have a U1 and U2. But normally, if we have, let's say, Aston model where volatility is stochastic, then we'll be only interested in a marginal density of a stock, not volatility. Volatility will play its role in the dynamics of stock, but it's not necessary to have that density of volatility derived. So following the definition of characteristic function, we have A, which is some constant term, or time dependent. It could be also time dependent, but it's state independent, so there's no dependence on x. And we have two terms corresponding to x1 and x2. So it's this term b1 and b2. And we have a terminal condition. So the final point, we have EIU x1t and EIU x2t. And this corresponds to the, of course, definition of the characteristic function. Okay, so this means that the boundary condition, the terminal condition are here as follows. So for A, we have a 0 because there is no constant terms here. And for B1, we have IU1. And for B2, we have IU2. Okay, so now we can use the A, B, A, C's, and R's to compute ODEs, ordinary differential equations. And so those would be very trivial actually in this case. So the B1 derivative of B1 to tau is 0, B2 to tau is 0, and then all the remaining terms are just derivative, the ODE for A. So if we just integrate, so you see there is no real tau dependence, so we can simply integrate, take into account the boundary conditions, and this is the expression we get. And so finally, the 2D characteristic function is given by this equation, where we have is given by this term in 12. So this equation can be substituted for A here, and for B we know it's IU1, and here we have IU2. So those two terms we know explicitly too. Although previously we have discussed affine diffusion framework, which only included Brownian motion, so there was diffusion in terms of Brownian motion, it is also possible to include jumps. Then we have so-called affine jump diffusion settings, so AGD. As you can see, the SDE that we consider, or system of stochastic differential equation, has additional term, which is J, and then we have a transpose because it can be also a vector, and then we have a the multidimensional Poisson process. So you can see that basically before we had the term, we had considered SDEs of this form. Now, once we include also jumps, then we have additional term. In the framework of affine jump diffusion, as we have already done it before, jumps are independent of Brownian motion. So there is an independence between diffusion part and jumpy part. So the jump magnitude is uh, is independent, and also we have independence in Poisson itself. So intensity of the framework does not depend on J. Okay, so now let's take a look at the conditions. So as in affine diffusion framework, all the drifts, squared volatility or covariance metrics, interest rate, they need to be linear. The same holds for intensity. So intensity of a framework, so psi, which is intensity for Poisson process, cannot depend, can in different way than linear on state values. So you see there we have L0 plus L1x, and this dependence is only linear. And then the characteristic function, similarly as we have seen before, so it's a discounted characteristic function. It's a minus, we have a discounting coefficient, IU UT, so this is the multidimensional variant of the characteristic function, xt. And then we have a already we familiar form that we have a plus b times x under risk neutral measure. So already as stated before, in this case, we don't consider interest rate to be stochastic is deterministic, so we can take it outside. Then we have only a characteristic function, not discounted characteristic function. And in case of jumps, we only need to check whether linearity in a state variables holds. Typically, models for jumps are not really complicated because handling jumps already in a very simple setting, it is troublesome, especially once we talk about calibration. Previously, we already have discussed the impact of jumps on implied volatilities. We could see that there is no really clear different effects of different parameters on a smile or skew. So there was a lot of interaction between parameters, and that makes it a little bit less attractive. On the other hand, by adding jumps, the biggest problem is with hedging, because if we have a continuous process, typically the derivatives are smooth. So we have a smooth problem. Derivatives are nicely behaving. Once we have a jump component included in a framework, typically there could be also a lot of volatility, a lot of fluctuations once we talk about sensitivities. This is why jumps are not typically the best performance. They don't have the best performance in terms of handling and calibration and also hedging. This is why later we will discuss stochastic volatility models, which also will which also will fit the class of affine diffusion. But right now, we look only whether the results we have derived previously for characteristic function for jump diffusion model, whether we can also derive those using framework of affine jump diffusion. So this is the condition. So obviously the model that we considered before, so it's a Mertens model, wasn't really involved. So this condition would be satisfied, and this is the characteristic function we can get. So the ODEs, so ordinary differential equations, similar as before, we have this term corresponding to linear interest rates, drift, and volatility. And we have also, maybe it looks familiar, expectation of e to power, and then we have a jump magnitude times b minus I minus 1. So this term we already have seen in the previous lecture when once we derived the characteristic function for jump diffusion model. And this term in particular was related to arbitrage freeness and also PIDs. This is where we have seen this expectation. Expectation in this term, it is taken with respect to jump amplitude. This means that B, it is not stochastic, so only stochastic variable is J. This is why if we calculate this integral, we have to take the integration with respect to density of J. So this amplitude, I also call it magnitude because it specifies how big the jumps will be. and those, you see those terms are in both cases for A and B essentially the same. The dimension of the complex valued ODs, so complex valued because we will have many i's, so it's a complex value for B and correspond to the dimension of that variable x. So already, as we have seen in previous example, B, size of B depends on how many SDs we have in our system of SDs, and U, size of U, depends on what output, what characteristic function, in which dimension we want to see it. Typically, U, it is one-dimensional, so U, it is maybe it's a vector of different U, so it's a U1, U2, U3, and so on, which would correspond to U of log, maybe I should just call it U of X. We have a U of, let's call it a variance, maybe. We have a U of jumps. Those typically would be set to 0 because we are not interested, in this case, in 3D characteristic function. We are only interested in a marginal distribution for log of stock. So this is why we would have only single dimension in this in the output for characteristic function. However, the dimension of B would correspond, even if we are not interested in distributions for variance and jumps, a dimension of B would always correspond to number of SDs we have. Okay, so let's take a look at the SD we considered before. So this is a stochastic differential equation for jump diffusion. So it's a Black-Scholes model extended with jumps. So this is, we have already derived this dynamics previously. And because we have a Q measure right now everywhere, you can see that there is additional term in the drift, which corresponds to the frequency, or this is the term from Poisson process, the intensity parameter, and then we have expectation of e to power j minus 1. So this expectation obviously is constant because we already integrated out. This parameter is also constant, so you see it is not in a it is in linear in state variables because it's trivially a constant. We also have derived PID, the partial integral differential equation, which is of the following form, and we can also clearly confirm that this model is not affine because we have s squared here by PID. If we look at this is the same case as we had for Black-Scholes, so we need to perform log transformation. Log transformation would give us the following differential equation. So it is simple again. We don't have any dependence on stock or x by diffusion and also by the jumps. So we have only j. This is also the details you can find in the previous lecture. And this term obviously is constant. So it's a rather trivial extension in this case because this j is just an independent random variable. Intensity is constant, volatility is constant, and drift is constant too under this framework. So this is what we have. So now the PID under x. So again, we switched from s to log of s. This is the following differential equation we have. And we know that the solution, the characteristic function, is given of the following form. So it's AB times x. We also have an initial condition. So it's a this is actually, you can see that in this case, we just consider characteristic function tt, so there's no tau here. So this is x0. After substitution, so after calculating all of the derivatives, so we have a derivative respect to tau, derivative respect to x and x squared, and this is the solution. So we can just calculate those derivatives as we have in this expression. And so we have here derivative, okay, so it's a phi x, derivative of a to tau, and b to tau, and the same as we have done for Black-Scholes case. And the only one term which is different is this expectation. We have characteristic function of x plus j, so this is here, which by definition would be just a plus b times x plus j. So if you can see that here we would end up with a characteristic function, so we have independence between x, so actually in this case x and j. So we have characteristic function of j, characteristic function of x times, because this is characteristic function of x is defined here. So it's basically this term. which is a b times x, plus times the expectation of exponent, and then we have this term bu tau times j. So this is what is left, right? Because also the expectation is calculated with respect to density of j, not x, of course. And x in this case was actually constant. So this is constant, can be taken outside the expectation, and we are only left with expectation of b times j and then exponent of that. After substitution, so as we have done again for Black-Scholes case, we end up with this differential equation. Then if we look at the terms by x, then we end up with this condition. So this term has to be 0. And then if we collect all the other terms and put it by derivative of a, this is the expression we find. And this expression we will also find using Duffy-Pan and Singleton, where of course you have to take into account that you have you have also C volatility, and also we have Xi or L0 and L1 for the intensity for the jump part. Again, this is rather trivial because everything is essentially constant here. So the condition, the solution for A is as follows, and you can actually check that is the same solution that we have derived previously without using affine diffusion assumptions. Just for simplicity, I also have included the coefficients. So you see, it's everything as we have seen before for a Black-Scholes case, except for constant parameter that we have for A0. And also we have L0, which is Xi. So this means intensity for our jumps is given by a constant. It is not state dependent.